Is Colin White, who's going to be talking about case-centered clustering under Perturbation Resilience.
Thank you, Avram. And thanks to the organizers for organizing this great workshop and inviting me. Okay, so I'm going to be talking about case-centered clustering under Perturbation Resilience. This is joint work with Nina Balkin and Nika Hakdalab. All right. So first, just a really quick overview of clustering. So clustering is a very common problem in unsupervised machine learning. And so we're given some set of elements that could be articles with different topics. And then all these articles have distances between them. The distances represent how close in subject they are or how different in subject they are. And then the high-level goal is to partition all these documents into k different clusters. And we hope that the clusters kind of model what the topic is of all these, of the groups. Okay, so we're going to try to minimize the distances within each cluster and maximize the distances between each cluster in some sense. So a common way to do this is using some objective function. Some common objectives are k-means, k-median, or k-center. Okay, now I'm going to get a bit more specific. So in this talk, I'll be discussing one objective called the k-center objective. And for this one, imagine that you're designing a city and you want to place k fire stations spaced equally throughout the city. And your goal is to minimize the maximum travel time. You have to go from any fire truck to any address, or for any fire station to any address in the city. Okay, so say we have all these houses. So to be a bit more specific, we're given a set S of n different elements and some distance metric between all the points. And then we want to choose k-centers from the point set S and then assign each point to their closest center. And these are going to be the clusters. Okay, and then the goal is to minimize the maximum distance any fire truck has to go from the fire station to the house. So this is we want to minimize the maximum radius, and that's going to be the cost function of any clustering. Okay, so for this example here, this is going to be the cost of the clustering, the maximum distance. Okay. One other problem I'm going to be discussing is a slight generalization of this problem called the asymmetric case-centered problem. And so for this, we're just going to relax the condition that D is symmetric. So it might take 10 minutes to go from one fire station to a house, but half an hour to get back. You can imagine rush hour traffic or one-way streets as where we might want this assumption in practice. Okay, so everything else about the problem is still the same. So we still have the directed triangle inequality. So the distance from some points P to Q is less than P to R plus R to Q. And now we have to be a bit more careful in how we define the objective. We're minimizing the distance from the fire stations to the addresses, where the order matters. Okay, we just have to be careful that we're consistent with how we define the order. Okay, is the problem clear to everybody? Okay. So now I'm going to talk about what's known about these problems in the worst case, and then pretty soon I'll get to beyond worst case analysis. Okay, so first of all, these problems are NP hard, so we're shooting for approximation algorithms. And so for symmetric case center, in the 80s, Gonzalez showed a 2 approximation, and there are a couple of 2 approximations for this problem. There's the famous farthest first traversal and some other ones. And it was also shown that this is the tight approximation ratio. So this is the best you can do for symmetric case center, unless P equals NP. Okay, asymmetric case center, on the other hand, is a bit trickier. So the first non-trivial approximation for this problem was in the 90s by Viswanathan, who showed a log star n approximation. So this is kind of a interesting phenomena because when this result came out, everybody thought, oh, for sure there must be a constant factor approximation of this problem because log star n is such a bizarre function class. But as it turned out, it took 10 more years of research and some sophisticated papers on multigraph, hypergraph coloring with gap hardness of gap instances, but it was actually shown that this result is actually tight. So it's kind of interesting that log star n is the natural approximation ratio for this problem. Usually we get either constant approximations or log n or something, but just an interesting side note is that it's kind of cool that log star n came out of a natural problem. Okay, but anyway, so this is what's known in the worst case for these problems. Any questions so far? All right. So now I'm going to define perturbation resilience. We heard Avram mention this a little bit in the first talk. And then I'm going to show results under this perturbation resilience assumption and how we can beat the worst case for these problems. Okay, so just a little bit of background, or a little bit of justifying perturbation resilience. So, sometimes log star n isn't desirable in practice because it's not even a constant approximation. And a lot of times these NP hard instances don't always match up with what we see in practice. So, I don't think there are any cities out there that have the intricate constructions used in the lower bounds. So even though there are some lower bounds, maybe we don't see them in practice. Okay, so for perturbation resilience, we kind of heard Avram explaining the intuition behind this at the start of the day. But the idea is that small changes to the data set, to the distances, shouldn't affect the optimal clustering. And we kind of justify that by saying if it does affect the optimal clustering drastically, then maybe clustering isn't the right thing to do. Maybe we won't get as meaningful a solution. So if you look at the data set on the left, say this is the optimal solution, but then if we just tweak the distances by a tiny bit, then we get a completely different clustering. So this would not be perturbation resilience. And you can think, if we go back to the example about the articles and subjects or topics, so maybe we don't really know what the topics of these points are because they're so close together that we don't really know what the right answer is. Whereas on the right, all the points are more spread out. So even if we move the distances by a little bit, the topics don't change. So it's kind of a more meaningful solution. Okay. Now I'm going to get a bit more specific. So the formal definition of perturbation resilience is that, so we're given a clustering instance, and we say that an alpha perturbation is when we're allowed to stretch out any distances we want by a factor of alpha. And then a clustering instance satisfies perturbation resilience if for any of these alpha perturbations we do, the optimal solution stays the same. Okay, so just another example. On the left, all the points are really close together, so this doesn't satisfy perturbation resilience. Whereas on the right, the clusters are more spread out, so it's kind of resilient to these changing the distances. Yep?
Does that also say something about uniqueness of the optimum under some perturbation? Is there some implicit assumption there? Or
Yeah. We assume that there's a unique solution, and then that doesn't change to any perturbations. Yep?
Surely what you just said can't be quite accurate, because if you choose alpha very, very small, even in the left case, it would still be alpha perturbation resilient, no?
Yeah. So in the next slide, I'll get into exactly what our goal is for this line of work, but you bring up a good point. So if you take alpha to be 1, then every single clustering is perturbation resilient. If you take alpha to be to 100, it's like huge amounts of structure. They're very far apart. So, yep.
You know my question. So, so what's the rationale behind taking the multiplicative perturbation rather than additive perturbation?
Yeah.
I want to model measurement errors, then it will be an additive perturbation, not a multiplicative perturbation.
Yeah, so there has been work on additive perturbation resilience too. There's also, I think there's been more work on multiplicative. So the way I think of it is all clustering problems are kind of invariant to scaling. So you could multiply everything by 2 and it wouldn't change the optimal clustering.
Everything is happening. First scale everything into the unit ball, and then you can talk about additive perturbation.
Yeah, so I guess if you scale everything first and then you talk about additive, I guess it makes more sense. To me personally, I can kind of see how multiplicative is natural just because of scaling thing, but I think, I mean, both of them are nice models. It's interesting for either way to define it.
I think in the additive model, so if you have an outlier that's far away, then when you do the normalization within the unit ball, then basically you get a very small average cost, right? And it seems that the structure of the problem is like scaled down by law by the outlier. So basically you need to be careful about how to do the normalization. And I remember that the result for additive, it's somehow like depending on the average cost of the data points in the instance. Right.
We have a efficient algorithm under additive perturbation.
Right.
I guess they just implied different types of structure. Okay, any other questions? So I want to make a couple more points. So one thing is, it's okay for the centers to change under these perturbations, because if we actually required the centers to not change, it would be much stronger, because if there are just a couple points nearby the centers, then we can kind of, under some perturbations, the centers would change. So we just want to make sure the clusters don't change. And then maybe one other thing I can point out is that we don't assume that these perturbations we make even have to satisfy the triangle inequality. So in this talk, I'll be discussing perturbation resilience where any perturbations, even without satisfying the triangle inequality, can be used. But there's actually recent work that's able to get around this problem. And everything in this talk applies to the new, weaker definition of perturbation resilience. Okay. Any other questions about the definition? All right. Okay, so now I'm just going to talk about what we do in this line of work. So this is going to be a promise condition. So we're given a clustering instance, and we're promised that it satisfies perturbation resilience. So as I mentioned before, for alpha equals 1, this would not be an assumption at all. But for alpha equals 100, it would kind of make the problem trivial, because all the clusters are like really spread out. So the goal is, how small can we make alpha and still come up with interesting results? So in particular, we're gonna be shooting for optimal algorithms. So no more approximation algorithms like the worst case, but our goal is how weak of a condition we can use and still get an optimal algorithm. So how small can we make alpha and still get an optimal algorithm? Okay, so now I'm just going to talk about some prior work in perturbation resilience. So this was defined in 2009 by Bilu and Lineal, and they studied max cut and showed root n perturbation resilience is sufficient to get an optimal algorithm. Then Awasi, Blum, and Sheffet studied center-based clustering. This is a general definition that includes k-median, k-means, and k-center, as well as it's kind of a generalization of clustering. And they showed an algorithm for 3 perturbation resilience. This was later improved by Balkan and Liang, who showed that just 1 plus root 2 perturbation resilience is needed to get an exact algorithm. And then there's been some more work on max cut, lowering the level of perturbation resilience, and minimum multi-way cut. And then a recent result a couple months ago, lowering the perturbation resilience needed for center-based clustering once again. And by the way, these are all for the symmetric versions of the problems. Okay, so for this talk, I'll be discussing exact algorithms for symmetric and asymmetric K-center under two perturbation resilience. So on the one hand, if we kind of compare these results, so what I'm going to be talking about doesn't handle K-median or K-means, but it kind of handles the asymmetric case. And also for the symmetric case, as we'll see soon, it's kind of a more general result. Okay. And then we also show a lower bound for K-center. So we show that if you assume anything less than two perturbation resilience, then it's impossible to get an exact algorithm unless MP equals RP. So this kind of shows that it kind of shows the exact level of perturbation resilience needed, where the problem switches between having a polynomial algorithm or being NP hard. So that's kind of cool. And then one other thing I want to point out is that this is the first time we're studying a problem that doesn't even have a constant factor approximation in the worst case. And it's kind of interesting that we just assume a constant level of stability, and all of a sudden we get an optimal algorithm. Okay, so now I'm going to first talk about symmetric K-center, and then get to asymmetric K-center, and then briefly mention the hardness result, and I'll also talk about more robust versions of perturbation resilience. Yep?
Is there some sense in which the approximation factor and stability, perturbation stability should be connected for, should be related for problems like K-center or K-median?
That's a very good question, and it leads to my next slide. But, okay, so for K-center, we actually have a nice theorem, which I'll explain. But in general, that's a very good question, and we're still trying to figure out the relation for problems in general. Okay, so for K-center, we can show that any two perturbation resilient instance will give the optimal solution for a two approximation algorithm. And this is actually, the twos here can be replaced with any number. So for any alpha perturbation resilient, any alpha approximation will give optimal. Okay. And by the way, this isn't true for general problems like max cut or even K-median. There's something a bit more specific about the structure for K-center. Okay, so the proof isn't too bad. I can fit it on a single slide. So, all right, so we're given some two perturbation resilient clustering instance. Say the optimal radius is R star. And then say we're given some two approximate solution. Say the red points are the centers of our two approximation. Okay, so now what I'm going to do is construct a two perturbation in the following way. First, I'm just going to multiply every distance in the graph by a factor of 2. And then I'm going to decrease some of the distances down. If they were greater than 2R star, I'm going to make them exactly 2R star. In particular, I'm going to decrease these distances between a point and its center in the two approximate solution C. Okay, so then what do we know about this perturbation? So first of all, it is a valid two perturbation. Nothing decreased because the distances in C were all at most 2R star to begin with. And so this is a valid two perturbation. And now I claim that C is actually the optimal solution in this perturbation I define. The way to see that is that, first of all, C is cost 2R star because it was originally cost 2R star because it's a two approximation. And then I increased everything, but the distances in C I decreased back down to exactly 2R star. And then if you think of any other clustering, well, it had to be greater than or equal to R star in the beginning by definition of R star. And then I increased everything by a factor of 2. So now anything else has to be greater than or equal to 2R star. Okay, so then that implies that C is optimal under this perturbation. And then using the assumption of two perturbation resilience, we can show that C had to be optimal originally. Yep.
These are for perturbations that do not need to satisfy the triangle inequality?
Yeah, but actually, so I'm not going to get to it in this talk, but there is very recent work that you basically take the metric completion of these perturbations we use in the proof, and with a bit more work, you can show it still works out. But this is recent work due to Makarichev and Makarichev, so this wasn't the focus of this work. Okay, any other questions? So this settles symmetric case center. So now I'm going to move to asymmetric case center. For this one, I'm just going to show some algorithm that gets the optimal solution for two perturbation resilience. Okay, so I'm going to start with a bit of intuition. So in the asymmetric case, it's kind of not as nice. So by definition, we know that the distances between all the centers to the points are r star, but the distance from the points back to their centers, we have no idea what those distances could be. So maybe there are some really bad points that are really far away going from the point to the center. And it turns out these points are going to give us a lot of trouble because they can sit really close to other clusters and make it really hard to distinguish the different clusters. Okay, so what would be really nice if we can kind of find a subset of points that exclude these bad points. And so that's going to motivate the following definition. I'm going to define a set A. And a point is in the set A. A point P is in A if for all other points Q. If the distance between Q to P is r star, then the distance from P to Q has to also be r star. One thing I should point out, when we're doing these algorithms, we can always assume we know the optimal radius r star, because if you remember from a few slides back, the r star value is just some distance between two of the points, and there's only n squared of them to try. So we can just brute force it in the worst case. Okay, so I define the set that kind of tries to capture the nice points, but you might have a couple questions right away, like, what if the set is empty? I mean, how do we know all of our points aren't very asymmetric? Okay, so it turns out, though, we can prove some nice properties about this set. And the first thing is that we can show that all optimal centers land in this set. So not only is the set non-empty, but we actually get at least 1 point per optimal cluster. So that's kind of a really good property to have. And then the other thing we can show, okay, so say the blue points are the optimal centers. There might be other points too. The other thing we can show is that for any point outside the set, the distance, or their closest point inside the set is in the same optimal cluster. Okay, so maybe that's a bit hard to parse, so let's look at a picture. So if you look at all the points outside the set A, the tan points, then if you draw an edge to their closest point in the set A, these edges are all going to be within optimal clusters. So there's not going to be an edge that spans an optimal cluster. Okay, I won't have time to prove these properties, but these two taken together actually give us a really nice property that it kind of reduces our problem to just finding the optimal clustering in the set of good points A. Because not only is there 1 point per cluster in this set A, but also once we optimally cluster A, we just attach all the rest of the points to their closest point in A. Then we get a clustering over the entire instance. Yeah?
Say the closest point in A, then that is the distance from P to the point in A, or the other way around?
Yeah, the first one. So
Okay.
yeah, I was kind of sweeping that under a rug. We have to be very careful when we define distances because we're in asymmetric. But yeah, you're right. Closest point, or distance from the point not in A to the point in A. Okay. Okay, so now I'm going to, in the next couple slides, I'll tell you a couple more useful properties, and then I'll show how these lead us to an optimal algorithm. Okay, so the first property is that for any point, the distance from that point to any center other than its own is greater than r star. So if we imagine some optimal cluster, the distances from the points outside that cluster to the center is greater than r star. Okay, and now the second property says that for any point, the distance from the center to that point is smaller than the distance from any point outside the cluster to that point. Okay, so this distance is going to be smaller than any point outside the cluster. The distance from anything outside the cluster to that point. And that's true of all the points. Okay, so now how can we use these properties to get an optimal algorithm? Okay, so here's the key observation. So what I want to do is take a ball of radius r star around the center. So from the first property, we know that this ball is actually an optimal cluster because it contains everything in the cluster and nothing outside. But we not only get that, we get something even stronger. So the second property shows this nice separation property where not only is it the optimal cluster, but everything inside this ball is closer to the center than anything outside the ball. Okay, so it's this nice separation property I'm going to call margin. Okay. And now let's look at what happens for a non-center. So let's take the ball of radius r star around a non-center now. This probably doesn't satisfy the nice margin property because if it contains a point from another cluster, then that point will be closer to its center, and the other center has to be outside of this ball from the first property. So we can kind of use these two properties together to show it doesn't satisfy margin. And there's one more case if we just got lucky and this ball had nothing from any other clusters, then it will satisfy margin, but that's also kind of a good case for us. Okay, so the takeaway from this slide is that if we take the balls around centers, they're really nice, but balls around non-centers are not so nice, and we can kind of detect this. So this implies the algorithm. So now I'm going to define the algorithm, and then on the next slide, I'll give an idea of why this is optimal. Okay, so we're going to start by creating the set A. We can do this in polynomial time if you remember the definition. And then for now, let's forget about the rest of the points. And now I'm going to construct these balls of radius r star around every point, and then I'm going to prune them in the next two steps. So first of all, if any ball doesn't satisfy the nice margin property, if there's a point inside the ball that's closer to a point outside the ball than to the center, then just delete this ball. And also, if any ball is just a subset of another ball, just delete the smaller one. Okay? And we're going to do this for all the balls. We only have a few left. And then I'm just going to add the rest of the points back to the cluster of the closest point in the set A. Okay, and then I'm just going to return these sets. Okay. Is the algorithm clear to everyone, first of all? Okay. So now why does this give us the optimal solution? Okay, so I claim that after step 4, we've optimally clustered the set A. And the first part is that if we look at the balls around the actual centers, these are going to be the optimal clusters, and they're never going to be deleted because they satisfy the margin property. And then if we look at non-centers, either they have points from other clusters, in which case they'll be deleted in step 3, or they'll just be subsets of the optimal clusters and they'll be deleted in step 4. All right, so now we've optimally clustered the set A. There's also another case if one non-center just captures its entire cluster, but then it doesn't really matter which one we choose. Both of them are the optimal clusters. Okay. And then if you remember from a few slides back, I said that at this point we've just clustered the entire instance. Because now we can just add the points outside A to their closest to the cluster of the closest point inside A. Okay. So this completes the proof. Any questions about asymmetric case center? Now I'll just very briefly talk about a couple other points in this research. So we get a nice lower bound which shows the level of perturbation resilience needed is tight. So we show there's no optimal algorithm for 2 minus epsilon perturbation resilience unless MP equals RP. And the reduction we use is from dominating set with a couple extra properties. So we need a hardness of dominating set even if there's at most one solution. So in order to do that, we use a nice result from Valiant and Vazirani, which shows a hardness of unique 3 set, and then we use reductions along the way that conserve the number of solutions. So that's kind of just a highlight of how we.
Quick question. Is it
Yep.
RP and not P? Is it because the reduction is randomized? Or?
So the Valiant Vazirani result about how 3 set is hard when there's at most one solution, that requires MP equals RP. That's kind of a randomized proof. But then we just like use that result out of the box, and then all our reductions are like deterministic. Okay. So now we kind of have this nice picture where if we look at the spectrum from alpha equals 1 to infinity, we know that there's no structure at the start, but then we kind of nailed down the point where the problem switches from having no optimal solution, no optimal algorithm to an optimal algorithm. Okay. All right, so now just very briefly, I'll talk about robust perturbation resilience. So remember the original definition, the optimal clusters aren't allowed to change at all under any perturbations. So you might think that's kind of stringent. So we have this new definition from Balkan and Liang, which now we have 2 parameters to tune. We have the alpha and we also have an epsilon. And we say that under any alpha perturbations, the optimal clusters can change by at most epsilon. So they can change a little bit. So in this picture, maybe this is the optimal solution, and then there's some perturbation, and maybe now this is the optimal solution, but only these middle points switch clusters. So the clusters are still almost the same. Okay. So it turns out in order to show anything at all, you need a lower bound, because if you don't have a lower bound on the optimal cluster sizes, then the problem is still hard, even for any value of alpha. And what we show is the very common single linkage algorithm, which is a very simple algorithm. The single linkage algorithm is just you start with n singleton points and just in every round you merge the 2 sets that are the closest together. It's kind of a natural algorithm for clustering. Yep.
And just wait, the lower bound is just because if you could completely eliminate one cluster, then all of a sudden you're trying to compare a K center to a K minus 1 center or a K plus 1 center, or is there more going on than that?
Trying to remember. So if you don't assume any lower bound on the optimal cluster size, you get an immediate reduction to just regular clustering. I think it's like if there's no lower bound, then you can kind of place K minus 1 points spaced out, and then just fit another clustering instance in the middle, and then you just have to solve that. Okay. So we get the single linkage returns the optimal solution under 3 epsilon perturbation resilience. So we can kind of think of this epsilon as it can't go above 1 over k just by the lower bound in the cluster sizes. Okay. I think I'm going to wrap up. I won't have time to explain the intuition behind this. Okay, so now just to conclude, So I showed a polynomial time algorithm for case center and asymmetric case center. I showed this is tight. So it's kind of really interesting from a theoretical standpoint because it's the first time we looked at a problem with no constant factor at all in the worst case, and just assuming a constant level of stability, we get an optimal algorithm. And it's also the first tight result in terms of the level of stability needed. And it's also kind of cool that in the worst case, we have these two problems that are like drastically different levels of hardness. One of them, there's an easy 2 approximation. One of them, no approximation to a constant. But just assuming perturbation resilience, the problems become equivalent in difficulty. So it's kind of a cool feature of this work. But then from a practical side, it's maybe not quite as interesting a result because we showed it's hard even for any value of stability less than 2. So there's kind of just a small window of values for which the problem's interesting. Okay, so now we have the lower bound for case center, but we don't have any lower bounds for k-median or k-means. So it's still an interesting question if we can go below alpha equals 2 for those problems. And then also, can we apply the symmetrizing technique to other problems? Okay, that's all I wanted to talk about. Thank you. Yeah.
I'm very curious if you look at actual case-center problems that people might encounter in practice, like the one that you mentioned at the very beginning to motivate your talk. Mm-hmm. How far are they from, to perturbation resilience?
Yeah, so this is a common question. Like, are problems in practice actually perturbation resilient? So unfortunately, we can't. It's NP hard to check whether a problem is perturbation resilient. People have different opinions about this. I guess in this work, we kind of motivate it by saying, like, if it doesn't satisfy perturbation resilience, then it's kind of maybe not the right thing to do anyway. But there's also I think there's some nice work about clustering biological sequences that Avram mentioned, where they actually do where they do kind of use these algorithms in practice and show encouraging results. I think sometimes if for like high levels of alpha, it's maybe not seen in practice so much. All right.
Yeah, just following up on that, we were saying that if your problem isn't perturbation resilient, then maybe this isn't the right algorithm to be using, or you're not really asking the right question. Do you think that really applies even for perturbation resilience in that 2 to 3 range? Or is it more about small perturbation resilience or really large-scale perturbation resilience?
Yeah. So, that's why I think the results I talked about are kind of really cool theoretically, but practically maybe not quite as much because, our algorithms are for 2 perturbation resilience. And there are other results for different assumptions where you can get kind of closer to like 1.1 perturbation resilience. Okay, yep.
So, I mean, even in the range of 1 to 2 perturbation resilience, do you think there's hope for at least a better approximation factor?
That's a very nice question. And I think that's what could be added to this line of work. So, like, we have some hardness results for finding the optimal, but maybe if we just assume low levels, we can get approximations. I think it could be cool to look at these recent Fox papers on finding p-tasses in planar graphs or doubling metrics and seeing if we can do the same thing for perturbation resilient graphs. Okay. Yep.
How does this lower bound relate to the lower bound of 2 for center stability?
Or center stability.
There is
the one by Shala?
And the raising.
Yeah. So we actually use, they use a reduction from perfect dominating set, I think. Dominating set with this added property.
Not the proof, but in terms of is one of them
so
related?
This is more general. It's a stronger result because Yeah, actually, I guess one of them doesn't dominate the other, but so their proof works for like k-median and k-means and everything, but center proximity is a weaker assumption than perturbation resilience. So in one sense, ours is stronger, in one sense, theirs. Any other questions?
All right, thanks.